Welcome everyone, and thank you for joining us for today's webinar, Crude Feedstock Optimization, Measurement Challenges and Opportunities. I'm Allison Sterling, Marketing Manager at Emerson Micromotion. I'm pleased to welcome you to our Emerson Flow Expert webinar series. Before we begin today, I just want to take a moment to acquaint you with your webinar environment. On your screen, you'll see a presentation window on the left side, a Q&A chat window in the upper right-hand corner, media player controls, and a resource box with related content that you can view and download during the event. You can resize, move, or minimize any of these windows during the event to fit your viewing preferences. At the bottom of your display, you should have a row of icons that also give you some added capabilities where you can share this webinar via social media or even request a visit from one of our Flow experts. Throughout the presentation today, we encourage you to interact with our speakers by typing in questions and comments using the chat panel, and we'll be answering all of these questions at the end of the presentation. And if for some reason we don't get to your question, we will be following up with any unanswered questions via email. We are also recording today's session, and we'll make a link to this recording available to you 24 hours post-event via email. On today's webinar, we are lucky enough to have joining us Julie Valentine and Don Miller. Julie Valentine has been with Emerson as a refining industry marketing manager for over 15 years. Julie is a graduate of the Colorado School of Mines and has authored numerous technical papers on various applications of flow technology in the refining industry and is a co-inventor in 2 U.S. patents for Micromotion. Don Miller is a North America sales manager for Rockstar Flow Assurance, onshore, offshore, and subsea. Don graduated from Texas A&M and has worked in the chemical analysis, petrochem, and oil and gas industry continuously for the last 15 years. Welcome, Julie and Don. I'll now pass it on to Julie.
Thank you, Allison. And I would like to also extend my welcome. Thanks for taking time out of your day to participate in this webinar. For the next 45 minutes or so, we're going to discuss the measurement challenges and solutions associated with the processing of opportunity crudes. We'll look at economic implications of utilizing these discounted crudes, and then an overview of some of the more common process challenges we hear from our customers. We'll then talk about several areas where the Emerson Flow Group has helped to provide solutions to some of the problem areas that we identified. We'll talk about various ways to characterize the crude, corrosion monitoring, crude blending systems, and also mass balance. And then we'll conclude with a summary and questions from the audience. So let's get started. So what are some of the major problem areas associated with the handling of opportunity crudes, and how do we maximize profits in light of these issues? The most common problems involve asset deterioration that's caused by excessive fouling or corrosion, process unit bottlenecks required slowdowns in operation, and a number of different safety concerns. Some of the problems associated with processing opportunity crude were expected, and some caught some of the refiners completely off guard. For example, there were locations in the crude tower that had never experienced corrosion issues, which were now seeing severe deterioration. The economic benefit of processing the opportunity crudes, though, is strong enough to justify working through the problems it creates. For a 250,000 barrel a day refinery, if you are able to substitute 1% more opportunity crude, this could save around $5 million per year in feedstock costs. The challenge then is how to process these feedstocks efficiently and safely. In this webinar, we'll discuss how accurate and dependable process measurements are a key part of the solution. Okay. This slide highlights some of the specific areas of concern. The problems ahead of the crude tower include variability in properties of the crude we're blending, fouling from waxes and filterable solids, asphaltene precipitation in the heat exchangers, causing throughput problems, emulsion instability in the desalter that could cause separation and efficiency problems. So there have also been frequent reports of corrosion problems at various locations in the crude tower and also in the overhead section. Because of the increased volume of the lighter components in many of these opportunity crudes, certainly including the shale crude, capacity limits of the overhead section are often reached. Also, as we change the crude that is processed at the front end, The effects trickle down all the way to the downstream units and even the final end product properties. So let's move on now and talk about some of the measurement technology available to help you to optimize operations with variable feedstocks. So I've broken out this seminar into 3 categories where measurement products can play a key role in giving refiners more flexibility and avoid some of the problems associated with the processing of opportunity crudes. The first area is characterization of the crude. We'll talk about more simplistic methods to evaluate the quality of the crude all the way to full characterization. The second part is about monitoring for corrosion and corrosion abatement. And then the third part is about a system of blending the crude to accurately and precisely meet the objectives of the refinery. So let's talk about crude characterization first. It used to be that refiners would run a single crude for long periods of time, so a crude assay was an effective means of characterizing the crude. But as refiners are now processing multiple crudes and blending different crudes, it becomes important to characterize each blend quickly and preferably online. Having a good understanding of the properties of the blended crude is critical for effective planning and scheduling activities and being able to match the target production plan. All of the downstream units can also be affected by crude changes, including even the product blending operations. So there are Emerson products that are used in what I term a simple characterization, and that includes viscosity, density, and also water cut. And I say simple characterization because these properties don't tell you the full story, but they can be used to look for specific areas of concern. Then I will give a brief description of a unique method of utilizing NIR technology in an online analyzer offered by a company that Emerson has a partnership with. So this is the story of a refiner who wanted to improve his knowledge of the quality of the crude that he was processing by getting an online viscosity measurement. The challenge that this refiner had was that many of the feedstock blends he was processing were what he called a dumbbell crude blend. And what is meant by that is if you looked at the distribution of the boiling range of the crude, it would be shaped like a dumbbell with lots of heavier components and lots of light components, but slim in the middle. As the distribution of components varies, what he found is that he couldn't effectively characterize the crude with the density alone, because for the same API gravity blend, his viscosity could be 25% different. The impact that this had was that they were reaching hydraulic limits in the preheat exchangers for the crude unit when the viscosity of the crude was higher than they expected. So knowing what the viscosity of the blend was, they could better characterize the crude, make adjustments to the blend, and improve the yield distribution and planning and scheduling effectiveness. What they found after several months in operation was just how important it is to accurately characterize the viscosity-temperature relationship. So let's talk about that. There are 2 methods used in the field for hydrocarbon applications. They are both based on the ASTM D34193 equation, which can be effectively used to calculate kinematic viscosity at reference temperature from the viscosity at line temperature. The first method is the equation method. In this case, the temperature-viscosity relationship can be characterized by a single curve or equation. Due to significant variability in the quality and character of different crude oils, this is not really an appropriate method for crude oil. It works well on products like jet fuel, but not on crude. The second method is a MultiCurve method, and this gives the user flexibility to select broad enough number of samples across the blends that he can use it to analyze and accurately represent the crude that's being characterized. So what is ASTM D341? It's the industry standard logarithmic equation that was developed to characterize viscosity of hydrocarbons at different temperatures. It applies to all hydrocarbon products, as it has been found to be an effective way to calculate viscosity at a reference temperature from viscosity at line conditions or vice versa. So the equation is used to find the values of constants A and B for each of the crude samples of the crude oil, and then calculate viscosity at reference temperature. So we established that the MultiCurve method is the appropriate method for crude oil. So let's take a closer look at this method. So the user can input up to 8 curves into the transmitter representing 8 different quality crude oils. The ASTM D341 equation, constants A and B, can be determined through laboratory calculation or by using viscosity data from the crude assay. Often the crude assay includes data of viscosity at 2 different temperatures, and it's this data that needs to be input into the transmitter. So the quality of the viscosity data collected is important to the ultimate success of the reference viscosity calculation. The programmed curve selection should include the range of composition that the meter is expected to see and in the appropriate temperature range that the viscosity is expected to be measured at. Digging a little deeper, when inputting the curves into the transmitter, it's not necessary that there is a curve for every exact crude oil blend. It is, however, important that you do cover the whole span of the expected crude quality. So curves 2 and 7 should be your high and low operating blends, and curve 1 and 8 should be the extremes, so that anything that might fall outside of the expected range will still give you a reasonable result. The middle curve should represent blends in between those extremes. It's also important for the accuracy of this method to make sure that the curves span the range that includes the process temperature and the reference temperature, and that the curves were developed for the particular product being measured. So, for example, you don't try to use a curve that's developed for asphalt on crude oil. Then if you look at the graph, the blue, orange, and red dotted lines on the chart explain how the calculations are performed in the transmitter. So the meter measures the line temperature and the line viscosity and places it on a curve, and then interpolates in between the 2 curves so that it will calculate the reference viscosity from the reference temperature on that curve. The reference viscosity can then be used to manually adjust blends or as part of an APC for the crude tower or as data input into planning and scheduling programs. Another measurement that is important for most refiners is accurate and reliable water cut. One of the problem areas that we identified in the beginning of the webinar associated with opportunity crudes involves emulsion stability problems in the desalter. Emerson's Roxar water cut meter is an ideal device to identify this problem. The Roxar water cut meter uses a patented microwave resonance technology to measure the permittivity of an oil-water mixture to calculate the water cut. And it compares the known permittivity of the hydrocarbon and of water compared to the permittivity of the mixture to calculate the water cut. And it can detect the water content changes as low as 50 ppm. This sensitivity is matched by no other full-bore technology, and it can be a valuable tool to look for problems in the desalter and gives the operator the ability to take the mitigating steps that he needs to. One of the problems that many water cut analyzers have is that the water cut measurement is affected by changes in the crude oil density. And one of the features of this technology is in the automatic adjustment for changes in crude oil density when used in conjunction with a densitometer or a micromotion Coriolis meter. Another unique feature is that it is the only full-bore inline measurement. So most water cut devices use a slipstream measurement, and a full-bore inline measurement assures a representative sample, and it's also not susceptible to issues related to scaling or wax buildup. So unlike other devices, there is also no periodic calibration in order to maintain the accuracy. And now I would just like to introduce the technology that gives you the ability to comprehensively analyze the crude oil properties. As I mentioned at the beginning of this section, the other methods for crude oil characterization help to identify specific areas of concern or identify certain quality parameters. But the Topneer system has the ability to give you everything you can find in a crude assay, including the complete distillation curve, yields, total acid number, API gravity, sulfur, etc. The Topneer technology is based on near-infrared spectroscopy. which has become quite well known in the industry for recent years. Each NIR spectrum is unique for each product and is the fingerprint of the sample. The main issue for NIR is in the modeling to identify the properties from the NIR spectrum. The model which most technologies use is complex and difficult to maintain. With the top-near approach, there is no model to maintain because it's a pattern recognition technology that uses a reference database for all of the properties. The technology searches for the closest spectral neighbors within the database and computes the properties as a function of the properties of its neighbors. This is an excellent tool to very accurately characterize the crude in order to optimize overall refinery performance from the front end of the refinery to the back. Let's switch gears now and talk about one of the most significant issues for processing opportunity crudes, which involves monitoring for corrosion. One of the interesting things we are finding is that even when blending the same two crudes, the ratio of each of those crudes affects the corrosion significantly. So having accurate ways to monitor the corrosion for each type of blend is important. Then having an effective process to mitigate the corrosion with inhibitors is also important, and we'll discuss this as well. So at this point, my colleague Don Miller, who is responsible for oxidized corrosion products, is going to lead us through this portion of the seminar.
Thank you, Julie. I'm going to cover the main points of corrosion refineries and where the Rockstar technologies can assist you with the detection and management of corrosion. Roughly 8 years ago, NACE did a study, or what would be a gap analysis for the U.S. government, and this little bit's taken directly from this analysis. The cost of corrosion directly impacts refineries' production capacity and profitability. The gap analysis report estimates profit losses ranging from $2 to $12 billion annually for the ceasing production due to performance maintenance due to corrosion. After a review of 82 corrosion issues unique to the refining industry, the gap analysis report identified 4 specific technology needs for the industry, which, if addressed, will directly reduce these costs. The 4 technology gaps identified in the report include corrosion knowledge management, corrosion prediction and modeling, corrosion damage assessment, and new materials. Identified within these gaps is the need to invest in corrosion prevention strategies, modeling and monitoring tools that can predict corrosion rates, update the standards, and update corrosion-resistant coatings. And if you see in the slide, as much as 36% of the maintenance costs in refineries can be linked to corrosion remediation and repairs. That's directly from Saudi Aramco. From that, this is for something to think about. We're dealing with this webinar with opportunity crudes. Well, what happens when you change your crude blend from load to load? Well, we're going to talk about that from a corrosion perspective here in the following slides. So let me go over the 4 main types of internal corrosion within refineries. We have water-related corrosion. Well, the crude oil desalting and distillation generates considerable amounts of wastewater, which contains H2S, CO2, chlorides, and dissolved solids. Also, cooling water used in the refining operations has various levels of corrosivity. The second main is processing-related corrosion. Crude units are highly affected by corrosion. Hydrochloric acid, carbon dioxide are the 2 most common corrosive agents. However, hydrogen sulfide, low molecular fatty acids, and sulfuric acids are also possible causes of corrosion in crude units depending on the type of crude that's being processed. Third is the naphthenic acid corrosion. Organic acids present in crudes can cause high temperature corrosion, referred to as NAC. Corrosion rates can be very high, and locations of these corrosion areas are difficult to identify without the use of various technologies. And fourth, we have sulfur. Sulfur is present in all crudes, in several forms as well. If its concentration is greater than 0.2%, corrosion will happen within carbon steel above 230 degrees centigrade. So, as we look throughout the various processing units, we all find different challenges to accurately monitor and measure the effects of corrosion. This is why Roxar offers multiple technologies in order to best apply the corrosion instrumentation. We offer both proactive options on the left side of the slide, which apply toward the need for fast, high-resolution fluid monitoring for immediate responses and therefore actions, as well as the long-term monitoring instrumentation that can provide highly accurate pipe wall measurements to understand the long-term impacts on your refining for your integrity management. And from that, we'll now go over each of these in a little more detail. Okay, let's take a look at the Roxar FSM, or the Field Signature Method. Roxar's Field Signature Method is the leading monitoring method for large surface areas and has been used commercially since 1991. FSM is highly versatile and can be operated on offshore platforms, on deep water pipelines, in refineries, on oil and gas production platforms, as well as in underground or even remote pipelines. The FSM measures corrosion or erosion by detecting small changes in current flow due to metal loss. With FSM, sensing pins or electrodes are distributed over the area to be monitored, with the typical distance between each measuring point of about 2 to 3 times the wall thickness. Then an initial voltage measurement is taken, and then subsequent changes in the electrical field pattern are detected and compared against the initial measurement to infer structural changes in the monitored area. As you can see, those small dots over that pipe in the lower right-hand corner of that slide. The system presents graphical plots indicating the severity as well as location of corrosion, calculates corrosion trends, and the rates. Both sensitivity and repeatability for general corrosion are typically better than 0.1% of the wall thickness of the pipe, which then means that the actual sensitivity increases over time as there are corrosion or erosion attacks continue. Here we're looking at our intrusive monitoring options that go above and beyond your typical weight loss coupon points. Although we do offer weight loss coupons, I'm going to focus on the online units for this webinar. From there, the Roxar system is made up of 4 main parts. We have 1, the access fittings and holders for the probes or coupons, the probes themselves, be it corrosion or erosion, or even combined units for doing both corrosion and erosion simultaneously, data loggers, which can be standalone, hardwired into your systems, or wireless, and then the retrieval units with valving in order to do online or live retrievals and implementation of new probes or coupons. But the main feature of the intrusive monitoring system is the intrusive probe. The probes are inserted directly into the process to monitor corrosion or erosion. A variety of different probes exist for different applications and conditions. So, we are now directly measuring the corrosivity of your process stream versus the long-term monitoring of metal loss with the non-intrusive technologies or even a coupon. So now for a quick poll for you guys about the type of corrosion monitoring technologies that you predominantly use within your facilities. If you would, please check off which one that actually fits best for you and hit submit, and we'll go over that a little bit more here in just a little while. But the first option is actually the non-intrusive pipe wall thickness, similar to FSM, the insertion probes or weight loss coupons, combination of the intrusive and non-intrusive, or simply the observation method during turnarounds where you visually inspect the innards of your pipework. I see things coming in here, and we're pretty evenly matched across all these. Still waiting on a few people here. We'll give you a minute or so. Well, we're waiting toward the industry standard here for the most part, which is the insertion probes or weight loss coupons. You can see some of the results here. The insertion probes and weight loss coupons are, again, yes, the industry standard and what everything was based upon. But one thing about the weight loss coupon is that it's an after-the-fact type of measurement, meaning that once you pull the coupon, you don't know what exactly had gone on and when it actually happened. It's just that it did happen. So from this point, we're going to look at the final piece of the Roxar corrosion monitoring system, which is actually field watch. With the earlier slides, we have seen how real-time data is accumulated from the available online corrosion monitoring solutions, and how we can ensure, how can we ensure that the data can be turned into valuable decision-making information? Roxar developed FieldWatch, a specialized Windows-based field monitoring system which enables operators to watch their areas remotely. FieldWatch is a system with modules with different monitoring applications of specific, or actually designed and has specific uses for corrosion and sand management, can be made available. The new software modules offer significantly powerful functions for the handling of large amounts of data from the various points, where you could have hundreds or even thousands of these corrosion points throughout larger facilities, and allows you to report and control it as a standalone facility overwatch unit. Multiple users can also access these modules simultaneously. This real-time data is also accessed directly via desktops and is all done via a standalone server type design. So what we get with FieldWatch is it allows for an easy collaboration and enhanced decision making, I should say, for the corrosion monitoring and any remediation strategies you have for your facility. So let's get proactive and win some of the corrosion battles within your refinery. What can you get when you immediately implement any Roxar or online corrosion monitoring points online versus a coupon? As mentioned earlier, blending opportunity crudes are a challenge. So what can be done to maintain or improve upon the reliability? Well, online we can verify that corrosion rates are within safety levels. We can provide more accurate input to risk-based inspection planning, which can extend out the lifetime of your critical assets, proactively monitor the effects of changing inhibitor programs online and immediately. And yes, we do offer all this, again, both either wired or wirelessly, both intrusively or non-intrusively. So from all these different points of going online, let's go over an actual application for you to look at with an opportunity crude blend. This refinery knew that they had increased corrosion issues when the weight loss coupon showed excessive mass loss. The question was when, where, how fast the corrosion rates were actually happening. So we were asked, and we installed one ER probe, which stands for electrical resistance probe, in place of the existing coupon, and combined it with a wireless logging system. Now they know when, where, how much, as well as who, as far as a provider of this opportunity crude, is being, or where it's highly corrosive. So if we look at the slide, over a 2-week span, the blue represents the blend being combined into the mainstream. So that's the load. The red line represents corrosion rate. So what we have, this is actually interpreted as a metal loss rate versus the actual corrosivity. So in the very beginning, we do have a slight slope, and then I highlighted one red dot to a next red dot. And you can see that the slope is quite high, and that is during this particular span of blending in an opportunity crude. Once that stopped, corrosion inhibitor was applied, and you can see that the red line went flat. So they were able to notice that the increased rate was there with this opportunity blend, and they were able to immediately remediate that with a different chemical or more chemical, and it settled out. So again, thanks everyone for your time on this, and I'll hand this back to Julie for the remainder of the webinar.
Okay, thanks, Don. Okay, so Don talked about different methods of detecting corrosion, and now we want to talk about the second part of the corrosion story, which is the corrosion abatement with effective and accurate dosing of inhibitors. So many chemicals are added with small injection pumps, and because of the pulsating nature of the delivery method, there's no apparent easy way to accurately measure the flow rates. A small micromotion Coriolis meter, though, is an excellent way to increase the accuracy of your injection system, as the flow rate can be maintained even with pulsating flows. The reason that accuracy is important is, of course, that underinjection leads to less than optimal corrosion abatement, but overinjection isn't good either. It can be costly, as these chemicals are often expensive. So the chart on the left shows a simple way to calculate the cost of overdosing, and this is a chemical cost of only $1.50 per liter. A meter can pay for itself in chemical costs alone, let alone the processing costs that can result from over or underdosing. After making any changes to the inhibitor injection rates or the chemicals used, we would then monitor or verify the effectiveness with the corrosion monitoring system and make continual adjustments as crude changes occur or process conditions change. So it's a complete system of monitoring and then dosing and then verifying that the inhibitor, either the inhibitor rates or the particular chemical that you're using is effective. And now let's talk about how flow solutions for crude blending. So early on in the seminar, I introduced the economic benefits for processing of opportunity crudes. For a 250,000 barrel a day refinery, a 1% increase in the amount of opportunity crude processed at a price differential of $6 per barrel gives $5.25 million. In order to take advantage of this price differential, the blend should be accurately controlled to a tight tolerance, which requires an accurate flow measurement. And this can be challenging with traditional flow measurement because most flow devices are significantly impacted by changes in the properties of the fluid that's being metered. So I would like to describe a case study for one coastal refinery in the U.S. who was challenged by their system for crude oil blending. Because of the variability in the physical properties of the crude, volumetric flow meters used to meter each of the blend components was unreliable. They were using a combination of orifice and ultrasonic meters. And because of this, the blending operators used tank levels to gauge the amount of each component since the flow meters were not accurate. Controlling to a precise ratio with this method was not possible. Also, they have 3 different crude towers at this refinery, and they couldn't draw from the same tank to feed 2 different crude units, or they would just completely lose their measurement. So they wanted more flexibility. Another big problem was that because of the poor measurement system, the crude oil storage tanks weren't always becoming empty when they were scheduled to be empty, and this had a detrimental effect on planning and scheduling and also on logistics. So this refiner installed 4 micromotion high-capacity meters to replace their ultrasonic and orifice meters. And they have a total of 10 crude oil storage tanks, and they have designed the system so that each meter can be fed from multiple tanks into the desired crude blend tank, including having 2 meters draw from the same tank into the into the blended crude tanks. So this gives them the flexibility they need for the blended crude into each of their different 3 crude units. The economic and process benefits that they realized were significant. Blending with the precise ratio of crude oil components allows the refiner to take advantage of the price differential between different crude stocks. When their planning and scheduling model gives them a target blend recipe, they can match each of the components to within plus or minus 0.1%. The second very significant contributor to the economic benefits was the decrease in demurrage costs. With the improved accuracy of the flow measurements, the storage tanks were becoming empty when they were planned to be empty, eliminating the demurrage costs. These 2 benefits alone amounted to reported savings of $1.5 million in just 5 months. There were also several process-related operational benefits reported by the refiner, which are more difficult to quantify, but they're nevertheless very important. The first was that the improved flexibility and more control of the feedstock, this led to better cuts and improved optimization in the downstream units. One of the keys to profitable operation of the refinery is the ability to always fill the vacuum unit and the coker. And with a more accurate blended crude, this is possible. Also, with more accurate cuts, other downstream units are able to run up closer to their unit constraints with less error from the planning model. And the last point, which again involves the coker, if the blended crude has too many heavy ends, there is a possibility of producing undesirable shot coke. This can result in a safety issue as the shot coke is released from the coke drum, or it can end up plugging the coke drum. As I mentioned at the beginning of the webinar, a changing feedstock has a rippling effect all the way through the refinery. It's likely that many of the properties of the process unit feeds and products will also be variable. This means it is often more difficult to get a good mass balance around the units. The process unit mass balance is a fundamental monitoring activity that underscores all other unit monitoring. I like that statement because it effectively communicates the premise that without a good mass balance, any evaluation of conversion or yield or efficiency of operation is at question. One can only know that the yield or conversion that is calculated is actually representing true operation if the data is validated by a good mass balance. So the target for the mass balance is usually at least within plus or minus 2%. The process for achieving that goal is a challenge. It involves taking samples for fluid composition or density and making sure that the samples are representative of the fluid during the test period. Then the meter correction factors are applied to the measurements to compensate for the difference between the actual process conditions and the design conditions. So there are a lot of sources of error there. So if we look at an example, if the specific gravity of a naphtha stream changes from 0.74 to 0.78, that will lead to a 2.7% error in the standard volume or mass flow measurements if the flow isn't corrected. In a refinery, we are never, of course, dealing with pure fluids, so changing specific gravities are what we need to deal with. This is why accurate flow measurement with standard differential pressure-based flow technology is so challenging, because it assumes a fixed density to be part of a constant meter factor. So why do we care if our flow measurements are accurate? What is the economic impact of improving the process measurements? Well, as we talked about in the crude blending example, there is a strong economic benefit related to accurately reaching production targets that are set by the planning and scheduling model. Also, operating decisions depend on having accurate data. So as one refining engineer put it, good monitoring provides the information necessary to increase product values and reduce operating costs. So one might argue that data reconciliation software can be used to balance and correct the flows. But in fact, accurate measurement works together with the software to give you better reconciled data. What I'm showing on the slide on the left-hand side is the effect of reconciling values based on more accurate measurements. So if we reconcile a 1% accurate meter with another 1% accurate meter, which is on the left side of the graph, the best reconciled accuracy would be 0.7%. If, however, you reconcile a 1% accurate meter with a Coriolis meter that is 0.1% accurate, you could improve the reconciled accuracy to 0.07%, which is 10 times better. So data reconciliation software works with the accurate metering, especially in strategic locations, to significantly improve process unit data. Let's take a look at a good example of this. This is on a hydrocracker at a medium-sized refinery in the U.S., and the challenge for this refiner was that the hydrocracker feed composition varied quite widely, and they wanted the flexibility to process different kinds of feedstocks. So the charge rate to the unit using a standard orifice DP measurement was estimated to be inaccurate between 2 and 5% because of the changing specific gravity. And this meant that the refiner was not meeting the target charge rates determined by the planning model. So the solution was that they installed an elite micromotion meter on the fresh feed to the unit. And they measured both the standard volume because the operators always will want to know what the flow rates are in standard volume units, the density online, and also the mass flow for the mass balance. They also bought the option of standard meter verification, which allows them to verify the accuracy of the device without having any interruption in the measurement. And with the long time between turnarounds, this was also important. So we can verify that the meter is accurate at any time we want just by the push of a button. So the result was that they increased their throughput on this unit by an average of 2%, and they were able to accurately reach their production targets and push up against unit constraints. The estimated payback for the meter installation was less than 3 months because of the ability to process more feedstock through their hydrocracker. So to summarize, opportunity or discounted crudes are just too tempting not to use, and competitors will also be using them, so most refiners choose to process them. The challenge is how to do it safely and efficiently. So we tried showing a number of different products that can be used to help avoid the problems and meet the challenges of processing up opportunity crudes. We talked about viscosity meters, water cut meters, corrosion monitoring technology, and micromotion Coriolis meters which are not impacted by changing compositions. So we tried to give you some ideas of how we can really improve this situation. So I want to thank you for attending this webinar. We hope that it was a valuable use of your time. And if there are any questions, we would be happy to address those now. Please remember that if we don't have time to get to your question, you can always use our Contact Me form to request a follow-up visit, or can send us either an email directly, either to myself or to Don Miller. And there is also additional documentation on many of the products that we discussed that you can download from the resources box. I will now turn it over to Allison to lead us through the Q&A session.
Thanks so much, Julie and Don, for all this great information. As Julie mentioned, we're now going to open it up for questions, so please use the Q&A chat window to ask the questions. And if for whatever reason we don't answer your question on the webinar, we will be sure to answer it via email after the webinar. It looks like we've already got some lined up, Julie, so I'll let you get to it.
Okay, let's see. One of the questions that just came in, how does micromotion meters help in cost savings for upstream crude production or gas treatment facility? That's a loaded question. What this particular seminar happens to be on the refining industry and all of these technologies that are used in the refining industry, and I have to say that personally, I am in charge of the refining industry, so I don't have a lot of knowledge for that, and that's a big subject. But what I can do is I can turn that question to some colleagues of mine that would be happy to answer that question, so that you can get sort of a more upstream crude production focus on where the applications are for micromotion meters. Okay, and then I see another question that came in. It says, what are the differences between Roxar's FSM technology that measures changes in pipe wall thickness and other technologies that seem to do the same thing? I think, Don, this might be a question for you.
Certainly. Well, some of the benefits of FSM include the ability to detect changes in corrosion rates much earlier than you'd say ultrasonic thickness testing, as well as it allows for a broader area, since the sensing pins are all interconnected and they do a comparative voltage comparison between them, and then with the FieldWatch software, you actually get a 3D grid of what's going on, not just in a generalized, but also possibly a localized corrosion or erosion event. The other option is that you can also do it across a weld bead, so you can actually monitor weld seams as well with FSM versus any other non-intrusive technology. Hope that answered that question.
Yes, thank you.
Perfect.
Okay, I see another question. It says, if the physical properties of my crude oil vary significantly, will this affect the accuracy of the micromotion meter? And the answer to this is no. That's really the whole idea behind having mass flow measurement and Coriolis-based flow measurement, is that it is not dependent on the physical properties of the crude oil. So if you have a very light crude oil, if you have, for instance, a shale crude, or you have a very heavy crude, it has no impact on the accuracy of the meter. So that's why it's so flexible to be used when you are switching crudes and you have a lot of variability in your crude oil. Okay, I see another question. It says, what is the lowest minimum water cut measurement, and what is the highest water cut measurement? So, Don, again, I think you might want to answer this one.
Yep, certainly. Lowest, in terms of detection limits, we're getting into the parts per million range. We're about 50 parts per million as far as detection range. Normally the ranges for, and we're getting into the uncertainty side of things, is we're 0.05% of water cut or water to oil ratio, all the way up to water saturated, which would be 100% water. So we've got a couple different, or 3 different designs of our water cut meters with the microwave resonance that can be suited for your flow regimes. So hope that answers the question there. I guess
yes.
We've got a sensitivity to change, but the lowest range of what we're looking into is about 0.05%. So
okay, perfect. Thank you, Don. Okay, another question came up. What is the pressure drop through a Coriolis meter for a typical crude blending application? Pressure drop, of course, is important for most refiners and most applications. And what I can say here is that typically we can design the system to be able to take whatever kind of pressure drop the system will allow. So, in other words, we'll choose the size of the meter so that we don't exceed the pressure drop limitations that we have in that system. So I would say in refineries, most of the meters that we end up sizing and specifying are normally within the 1 to 3 psi pressure drop range, because most applications you don't want to take any more pressure drop than that. So it's definitely very, very possible to have a very low pressure drop through a Coriolis meter in these applications. And I think I'm not seeing a whole lot of additional. There is one question here, another question about does chloride carry over is observed in natural gas compressors? And again, I'm not quite. We'll have to get back to you. That whoever the gentleman that asked this question, I think we want to get back to you on the answer and maybe clarify the question a little bit better. That we can.
I think we might need a little more information on that one.
Yeah, we need a little more information than that. But I think that's all the questions that have come in at this point. So, Allison, do you want to take it back?
I will. If you guys think of any other additional questions we mentioned, please don't hesitate to contact us via either the email addresses that are on the last slide here or via the Contact Us button at the bottom of your screen. Thank you again for joining us today. We will be sending out a link to this recording via email tomorrow, and along with that, the links to also the additional resources that you see on the right side of your screen. On behalf of our guests, Julie Valentine and Don Miller, as well as everyone at Emerson, we thank you for joining us and taking the time to view our webinar. Have a great day. Thank you.